Hi everyone, I'm Yogesh, a PhD student at the University of Illinois Urbana-Champaign, and today I'm here to present our work on vision transformer and electromyography-based method for local fatigue assessment in construction workers. So if we look into the very nature of construction works, then it's like physically intense. There's a lot of repetitive tasks and very awkward posture. So construction work is like one of the most physically demanding works when we compare with like you have to carry a lot of heavy stuff, a lot of material handling, and then the posture is awkward. So this can lead to several health problems, including chronic fatigue, work-related musculoskeletal disorders, and even mental stress. So if we look into like the current approaches that are used to assess fatigue levels in construction workers, most of them are based on surveys and questionnaires like the fatigue severity scale or the Borg RPE fatigue impact scale. So the major limitation behind these methods are they are like highly subjective. It's very intrusive. You go, someone is working on the field, you can just go and ask them, "Oh, how are you feeling?" And it cannot be done in a continuous way. And then it has a lot of reporting bias because every person has a different scale of how much fatigue they feel or how much pain they feel, and it's intrusive and non-continuous. So this is where physiological sensing comes into play. Electromyography is an electrical method where we capture muscle signals. So whenever we move, whenever we do any activities where muscle is involved, there is a neuromuscular activation that like basically moves our body. And electromyography captures those signals during muscle contraction and relaxation. And this very signals, this information can be used via machine learning algorithms to assess physical fatigue level in the construction workers. So if we look into the current methods, so one of the major limitations is the feature extraction. While electromyography has been used to assess physical fatigue level, most of the methods are based on manual feature extraction. So it's like a basic signal. You have time features in time domain and frequency domain. So people extract like mean average amplitude, mean average frequency, and then use those manual signals on various algorithms like ANN or regression, SVM, or decision trees to make the decision. And another one is limited spatiotemporal modeling. Like if you're using extracting features, then either you use some spatial relationships like in artificial neural network, you are only looking into the particular location of the data. And if you use LSTM, then you are only looking into some temporal characteristics. So the current method do not provide both spatio-temporal representations. So our assumption is maybe a spectrogram and transformer combined framework can provide a means to model spatio-temporal features in EMG signals while automating the feature extractions. So I'll explain in more detail why this method works. So to summarize, our problem statement can be summarized as limited input information, modalities, and subjective scale can hamper the performance of physical fatigue estimating machine learning models. And thus the objective of this study is to develop a neural network-based model where we are modeling spatiotemporal features and one model of physical fatigue in a localized level. So the first part of the study is where we basically acquire EMG signals and use some amplifier to get the actual EMG signals. Now this is where the first limitation is fulfilled while. So we're talking about spatiotemporal modeling. So here we use short Fourier transformation to take those EMG signals and then have information in both temporal and spatial region. So we do a simple STFT and then we get an image. Now, the reason why we are going for an image is because we want to use a very advanced machine learning model which can work directly on image rather than using it on temporal signals. And so for this, we use a vision transformer-based model where we use the spectrogram as an input to the model and then the physical fatigue levels as the output. So basically, it uses the attention mechanism, which has really worked good for language models into an image thing. So to validate our method, so first we need to train the model. So for this, we use experimental roofing tasks where we had subjects performing roofing tasks. So For this one, we used the biceps muscle and the muscle in the arms. So we used two hammer sizes, and we had like 35 trials. So like each trial was each person hitting a nail for 5 times, and then they provided a verbal assessment in the Borg RPE scale. So there are three levels: low, medium, and high. So the RPE scale is between like 1 to 20, something between like less than 9, we considered it as low. From 10 to 15, we considered it as medium, and more than that, we considered it as high. So after every 5 trials, the subject was asked about how they are feeling, and then they have different verbal anchors like "I'm not tired," it's similar to resting, or "this one is the hardest thing I've done." And based on those verbal anchors, we're noting down the scales and how we have EMG signals, and then we have the levels. And then we train the model. So for the high fatigue estimation, we were able to achieve an accuracy around 82% recall. And for the arm muscle, which is like the brachioradialis, we were able to achieve around 78% recall. So the accuracy is around 75% for both of these muscles. So this is localized muscular fatigue assessment. So if we look into the confusion matrix, then when we are predicting a medium fatigue, then we have a bit not so good performance. It's around 72%, but for low and high fatigue assessment, it's above 80%. And we also compared the same data that we had with the SBM and ANN and random forest model, which are like more used in the literature. And the overall improvement is in the range from 25 to 46%, which is a significant improvement. So thus this study presents novel method for local physical fatigue assessment using business transformer-based method using electromyography. So by enabling proactive interventions, we hope that this such kind of systems can help prevent injuries, optimize task assignments, and improve overall workers' fatigue assessment and safety. So future research can focus on integration of other data sources and can look into a larger data source and more muscle group, as in this one we have only focused on the muscles of the hand and only on hammering task. And in the end, I would like to acknowledge our colleagues and our funding agencies. Thank you.